Welcome. So we're looking at the last part of Chapter 6, which is looking at the Solow model. Again, the point of this chapter is trying to explain economic growth in the long run and really thinking about how economies are better off over very long periods of time. So in previous videos, we looked at the basic framework of the Solow model and also looked at the basic mechanics of the Solow model and the steady state. So this section of the chapter really is designed to look at what changes the steady state and what kind of factors can affect the steady state, and by extension, what affects our standard of living. So if you recall, we have this basic framework for the Solow model where we have investment is balanced by the amount of capital that's being depreciated. So in the steady state, we're at some level of capital K star. And the basic punchline is that once we get to that point, then the economy doesn't change from that position. And so that's the steady state at that level of capital K star. And in addition to that, we have at that level of capital K star, as you recall, the level of output or output per worker or per capita is given by this level there, Y star. And so that's the basic framework for thinking about this Solow model. And so the point of this chapter really is to think about when some of these things change, for instance, the savings rate, or we'll look at total factor productivity, we'll look at how this thing might change and how all of those things will affect our understanding of this equilibrium. So as I said, in this video here, in this section, we're going to look at changes in the savings rate, changes in the population growth rate, and also changes in total factor productivity, or that parameter A. And so, again, the important implication for this is thinking about changes in the steady state and the extension of that, which is, well, when we change the steady state, we change the capital, the steady state level of capital per worker, which by extension could impact our standard of living through changes in the equilibrium level of output per person. So we're going to look at changes in the savings rate first. And so we're going to look at an example where we assume that there's an increase in the savings rate. And so to do this, we're going to switch to the smartboard. So here, our example, we're increasing the savings rate. And so we start off in this initial steady state. We have an initial level of savings S1. So our savings rate is going to increase from S1 to savings rate S2. And so in this picture here, again, what's going to happen is that's going to rotate up our investment function so that our investment function looks like this. So that investment function rotates up. And so, of course, what that gives us is a new steady state level of capital where that investment line intersects the depreciation line. And that, of course, also means we have a new steady state level of output per person. And so, like we talked about with the mechanics in the previous video, once our steady state changes, then that means we're going to move towards that new steady state. So if we're initially here at point A, then what's going to happen is over time, at that point initially, the amount of investment per worker is going to be greater than the amount of capital that's being depreciated away. So over time, if you're investing more than what's being taken away in depreciation, the capital stock is going to rise. And so as the capital stock rises, we increase the amount of capital, and we move towards that new steady state level of capital K2 star. And of course, what that also means is that as that capital stock rises, the amount of output per worker is going to be going up over time to the point where we move from our old steady state level of output per worker Y1 star to the new equilibrium steady state level of output per worker Y2 star. Okay. And so the basic mechanics here again is that the investment function rotates up. We move to a new steady state level of capital. And the important story here is that we end up at a higher steady state level of output per worker, which means our standard of living has increased. So the first punchline, and we'll summarize this at the end, is that higher savings rates lead to higher standards of living. And again, the very basic idea is that if we're saving more, then we're allowed to increase the capital stock more, which means we're going to be able to produce more output, with our given resources, and therefore output per worker is going to rise. So that's the savings story, and this is basically the same story that I just told you. Our savings function increases, that rotates that investment function up, and we get that new steady state level of capital. And not shown here is our increase in output per person. And one other thing to note here is that this shows you what happens to capital and output over time. And so you can see that if we're initially at that initial steady state K1 star, that's our initial level of capital per worker, then at time level T equals 0, we assume that that savings rate rises. And that's when we move to that new steady state level of capital K2 star. Okay, so as I said, over time, the level of capital is going to gradually gravitate to that new steady state level of capital K2 star. And you'll recall in the graph on output, again, we start off at our initial level of output per worker, Y1 star, and over time, as the capital stock grows, we move towards that new steady state level output per worker, Y2 star. And so eventually we end up at that new higher level of capital and output per worker with the higher savings rate. So the next story is to look at population growth. And again, we assume in this model that population growth is exogenous, but that doesn't mean that we can't fool around with it and change it, because as it turns out, and as we'll see, population growth has an important bearing on our understanding of standard of living. And so the idea here is, in this basic Solow model framework, the amount of capital per worker is the thing that's determining the productive capacity, right? The little k, capital per worker. So that's really determining our productive capacity, and given this production function, it's determining our standard of living in terms of output per worker. And so if we have population growth, then the idea is that the workforce, the amount of people in the labor force, is actually going to be growing proportionally with the population growth. And so the implication there is that as the workforce grows, holding everything else constant, that's going to be diluting the amount of capital that each worker has. So if the workforce is growing more rapidly with a given level of capital, that's going to be spreading an existing capital stock out over more workers, and therefore you're going to have less capital per worker. And so you have this dilution of the capital stock as a result of population growth. And so this implies an additional channel through which we can reduce the amount of capital per worker. As before, we talked about depreciation reducing the amount of capital per worker, but now we have this population growth as an additional way in which the amount of capital per worker is being reduced. So when we put those two things together, again, and we revisit this basic framework of capital accumulation, there's two factors which are playing on it. So on the one hand, we can increase capital through investment, just like what we saw before. If we're adding more to the capital stock, then that allows us to produce more output in the future. And so just like what we talked about before, investments in this model is determined through this investment function here. And then we can decrease the capital stock. Again, the capital stock is capital per worker here. And so we talked about in the standard model, we just looked at depreciation, but now we're adding this population growth factor. So when we put both of those things together, the total amount of reduction in capital per period is just going to be the sum of the depreciation rate plus the population growth rate multiplied by the capital stock. And so we have this revised capital accumulation equation which says the total change in the capital stock is going to be given by how much we're adding to the capital stock. This should be a minus. Sorry. That should be a minus right there. Minus what's being taken away with the effects of population growth and depreciation. Okay. And so just like in the basic model, we have this depreciation and capital dilution factor, which is just a linear function of capital. And so where that line crosses our investment function, that's going to represent the steady state. So if we add in population growth, it's really not much of a difference in terms of how we interpret and understand the basic Solow model, but it allows us to extend some of our knowledge and results in terms of the implications for the standard of living. So again, the easiest way to think about this is to go through an example. So again, if we assume an increase in the population growth rate, then we can see what happens to our standard of living. So if we go back to the smart board, so if we go back to the smart board here, again, we're going to assume that we're going to increase the population growth rate from N1 to N2. Okay, so this could be from 3% to 5% or something like that. So again, we start off in our basic framework here. There's our initial population growth rate plus depreciation. So we have this depreciation line, N plus delta times K, or N1 plus delta times K. So what happens is when the population growth rate rises, then of course the sum of population and depreciation goes up. And what that means, of course, is that the slope of this depreciation and capital dilution line, it should be, sorry, let's get this right the first time. The slope of that capital depreciation and dilution line is going to get higher. And so what that means is this line is going to get steeper and rotate up. And so, again, in the basic interpretation, what happens here is you're going to have, it's pretty obvious to see that you're going to have a decline in the steady state level of capital. And of course, what happens is once this depreciation line rotates up at this initial capital stock here, immediately you have a situation where the amount of capital that's being depreciated away is greater than the amount that's being invested in new capital equipment. So immediately you have the net effect of more capital being taken away in depreciation and capital dilution than there is being replaced through investment. So over time, you would expect the amount of investment in the net investment in capital to go down. Capital stock is going to fall. And so as the capital stock falls, we gradually move along until we end up at that new steady state level of capital K2 star. And of course, we can look at what happens to output. Again, as the level of output, as the level of capital declines to this new steady state, again, you can see that the amount of output per person or per capita is also going to be declining eventually to that new steady state level of output Y2 star. Okay. And so again, to summarize here, what happens is you have this population growth rate increasing that steepens that depreciation and capital dilution line, which gives us a new lower steady state level of capital, as well as a lower steady state level of output per person. So the punchline here is that if we have higher population growth, then that's going to reduce our standard of living, or reduce our amount of output per worker. And the intuition is pretty simple. The idea is simply that you can increase production by adding more workers in the labor force, but because of diminishing marginal returns to the production process, you're not going to get as much output out of that increase in labor as you would just a pure increase in labor. And so that's why you get a reduction in output per worker. Said differently, we can increase production, but it's not enough to compensate for the higher amount of people that are in the economy and workers in the workforce. And so even though output in total might go up, you're spreading it over a larger amount of people. And so overall, the amount of output per worker declines over time. And so this is one of the reasons why countries with traditionally high population growth rates might be interested in trying to lower the population growth rate, because you get a result, the opposite of this, where lower population growth rates should result in overall higher amounts of capital per worker and hence output per worker and a better standard of living. So that's the population growth rate story. Again, if we summarize here, this is just the picture without the production function, as I mentioned before, that population growth, the capital dilution line shifts upward, and we get a lower steady state level of capital. Now, if you look at what happens over time, again, you can see that if we start out, if we start out in this initial capital, in this initial steady state K1 star, then at time T0, we assume that there's this arbitrary increase in the population growth rate. As we saw, what happens is over time, the amount of capital falls. And of course, eventually we reach that new steady state level of capital K2 star. And what we saw with our level of output is we started off in this initial steady state level of output Y1 star right there. We have the increase in the population growth rate. Over time, the capital stock falls. That means overall the steady state level of output is going to be declining over time. And we end up at that new steady state level of output Y2 star. Okay. And once we get there, of course, we just stay there forever unless something else changes to move us again away from that steady state that we're at. So the third basic example is looking at the effects of total factor productivity, or TFP. And that, again, is through this A parameter. So here we're going to assume that there's an increase in total factor productivity or an increase in that A parameter. Now, we're not going to talk about where or why that might occur. We're just going to assume it's going to happen. And I'll talk at the end of this about interpreting total factor productivity, where it comes from and why it's important. So again, if we go back to the smartboard, so again, we have our initial setup here. Oops. We have our initial setup here. And so we're going to assume that total factor productivity is going to increase from A1 to A2, okay? And so there's actually two things that happen in this graph that are going to lead us to this result, why TFP, total factor productivity, is so important to growth. So you'll notice that TFP shows up in both the investment or savings function, the investment function rather, and also the production function. And so when total factor productivity increases, it's going to affect both of those things simultaneously. So what happens here is the increase in A, again, holding capital constant, means that our investment function is going to shift up, but it also means our production function is also, our production function is also going to rotate upwards, okay? So where do we start? Okay, so what happens is our new steady state level of capital is going to be there. We know that, so that's where the new investment line intersects that depreciation capital dilution line. And so we're going to go from point A to point B eventually. That also means we're going to go from point A up to point B here in terms of output. So again, we're starting out at this steady state here. We increase total factor productivity. This raises our investment function. Our new steady state level of capital is going to be here at point B. So what that means is that over time, our steady state level of capital is going to gradually increase until we get to this new steady state level K2 star. And at that steady state level of output K2 star, the level of output is going to be at this point here. You just read it off the production function. That's going to be equal to Y2 star, okay? Now, here's the point that's crucial to this story, right? This change, this capital adjustment process, this happens over time. And so the immediate impact of this increase in total factor productivity is to move our production function at this level of capital here, our production function and the amount of output that we're producing is going to immediately shift up to what we'll call B prime. And so what that means is that when we have this initial increase in total factor productivity for an existing capital stock, the amount of output is going to go up. If we're holding capital constant at that immediate point in time and we simply adopt a more efficient production technique or new technology, that's going to allow us to produce more output with our existing inputs. And so you get an immediate increase in output per worker, which puts us at this point Y prime. And then over time, what happens is these basic mechanics where the capital stock is going to rise over time, and it's eventually going to end up at K2 star. And so over time, as the capital stock rises, we then move along our production function to point B and output level Y2 star. And so this is the important, crucial part of it. There's two pieces of growth that happens with an increase in total factor productivity. You get an immediate increase in output per worker once you adopt this new technology, once the TFP actually becomes apparent in the economy. Holding capital constant, it makes production more efficient, and output per worker immediately rises. But over time, there's another effect, which is the capital stock grows as a result of higher output leading to higher savings, which leads to higher investment and increases in capital stock over time. So as the capital stock grows, output per worker grows over time as well, till we get to that new steady state level of output per worker. And so that's the beauty of increases in technology and TFP, is that you have this sort of double whammy. You have an immediate effect of increasing output per worker, and then you have a gradual effect over time getting to that new steady state where capital accumulation occurs, and that also leads to higher TFP. And so that's one of the basic stories behind why TFP and excuse me, and increases in technology are so important to the growth story. Oops. Which, is it this one? Okay. So again, this is just the picture without the production function that I showed before. And then the important point here sort of underscores what I just talked about, where we have this initial capital stock K1 star. Whoops. We have this initial capital stock K1 star. And at time t equals 0, we end up increasing total factor productivity that leads to a higher steady state level of capital. So over time, our capital stock grows until we hit that new steady state level K2 star. But the magic happens with output. As I said, we're at this initial steady state level of output per person, Y1 star. At t equals 0, you have an increase in TFP. In that A parameter. So the production function jumps upward at a given capital stock, which means you have this immediate upward jump in the amount of output per worker. So that's what I referred to as Y prime, I think it was. But then over time, the capital stock grows, and then you have an additional increase in output per worker, which eventually leads us to that new higher steady state level of capital, Y2 star. Okay. So there's a few pieces of the puzzle to bring away from this somewhat complicated, but also very basic in some ways model of the Solow model. So the basic idea here is that the Solow model in its basic form allows us to say some basic things about what we see in the real world with the data. So holding everything else constant, that is ceteris paribus, countries that otherwise look alike in terms of savings, in terms of technology, in terms of population growth, but have different starting levels of capital should converge over time. And so in one of the previous videos, we looked at a picture of output per person over a really long period of time, and we saw countries such as South Korea and China and India to a lesser extent sort of breaking through the low-income group and into the higher-income groups. And so that sort of comes along this idea that countries that have different starting points will eventually converge over time. As I mentioned in the previous video, the evidence on that is a little bit mixed, but it also depends upon some of the other factors that we're talking about here, and the fact that we can't necessarily hold all those things constant. Countries with higher savings rates also enjoy a higher standard of living. Again, increases in savings increase that investment function upward. We get a higher steady state level of capital, which leads to a higher steady state equilibrium level of output per person and a higher living standard. Countries with higher population growths have lower standards of living, as we saw in the example, that again steepens that population and capital dilution line. You get a lower capital per worker in a steady state and therefore a lower output per person. And then the other big point is that countries with higher TFP have a higher standard of living. So more efficient production and technology allows us to produce more with a given input. And so when we have jumps in TFP, we get this double whammy effect of an immediate increase in output per worker and then growth in the capital stock over time, which also increases output per worker out into the future. So that's the reason why with TFP, that's a really important channel for understanding and increasing the standard of living over time. And so the basic framework here of the Solow model says that if we hold all these factors constant, once we get to a steady state, then we never move away from that. And so the implication is that we grow for a while till we get to the steady state, and then we just stay there and there's no growth whatsoever. And so the punchline here is that this Solow model assumes that all countries eventually are going to stop growing. And so the limitation of this basic framework suggests that you can't, it doesn't allow us to explain sustained growth in the standard of living over time. And so if you look at countries like the US and other countries, you see long-run growth of 2 to 3% over really long periods of time, decades and decades, and this model can't seem to explain that. And so the way we get around that and enhance this basic framework is what's referred to as endogenous growth theory. And so the basic idea is trying to understand and explain how variations in total factor productivity occur across countries and over time. And in particular, the idea is not to assume that TFP is exogenous, but TFP is determined within countries based on things like institutions, law and order, the effectiveness of courts, the ability to start businesses, the infrastructure. All of those things go into thinking about how countries produce goods more and more efficiently and get them to market. And so the idea of this endogenous growth theory is simply that TFP is no longer assumed exogenous, but it's something that's determined within the model framework, just like in this setup here where we assume that capital accumulation is determined within the model framework. So it's a bit more complicated than this basic Solow model story. And there's chapter 7 is devoted to that particular enhancement to this basic Solow model framework. Thank you.